Today we're going to talk about measuring the quality of a survey. So in the last section, we talked about statistics, which come from samples, are used to make estimations about populations. These estimations we're going to use as we're going through these next few sections. When we were talking about taking these samples to make estimates about our populations, we said that there were potentially sources of bias. We talked a little bit about measurement bias and sampling bias in the previous section. In this particular section, what we're going to do, we're going to talk about a couple of questions. How can we judge whether our estimators are working, and what separates a good estimation from a bad one? So as we're going through this, we're going to talk about, again, a couple of key vocab words and talk a little bit about sampling distributions and some simulations and some basic results that we can come up with in the end. All right, so as far as evaluating surveys go, right, what we're going to do is we're going to talk about how we actually evaluate the method used for the survey, not necessarily the outcome of the single survey. Right, so the method, do we have a simple random sample? Are we finding ways to avoid bias? Are we getting results that are representative of our population? So we're looking at the method, not necessarily the single outcome. Right? If a group of researchers were to survey 1,000 randomly selected people, we would expect the results to vary from sample to sample. Right? As we saw in the last example in the last section, if we do different simple random samples, we're going to end up with different results, which should be the case. Because we would want to know how the group did as a whole, again, we're going to evaluate the estimation methods, not the actual individual responses or individual estimates. All right, so our goals for our estimation is two different things. So our first goal is that our estimation method should be accurate. Right? The method measures what it is intended. It correctly estimates the population parameter. Right? So accuracy, we're thinking about whether or not it is correct. Right? It is unbiased. The other thing we want to look at is whether or not it is precise. Right? If the method is repeated, the estimates are very consistent. Right? So we are looking at two different things, whether our estimates are correct and whether or not they are consistent. All right, so down at the bottom of this page, we have an example, all right, kind of a visual example. Our goal is to get the golf ball in the hole, right? If we're golfing, that is the ultimate goal. Which of these pictures shows a method that is accurate, precise, or both? If we look at this first one is both, right? Here we see both accuracy and precision. We see accuracy. Again, accuracy again measures or decides if it is a correct estimate, right? It measures what it is intended. And then precise means it's very consistent, right? So in this case, accuracy would be actually getting the ball in the hole. And then the precision is that, well, even the ones that missed, right, don't miss by much. It's very consistent results. All right, for this next one, looking at these different golf balls, these are clustered close together, right? So in this case, that exhibits precision, right? They're consistent. They're consistently landing in the same area, right? However, these are not accurate, right? Not accurate would mean it was actually going in the hole instead of all of them landing next to the hole, right? So we're going to say that this does exhibit precision, because they land close together, right? It is consistent, right? But not a good example of accuracy. This shows poor aim. Okay. So we do have precision because they are close together. Our results are consistent. However, they are not accurate. This last one, we're going to say does show accuracy, because here they are centered around the cup. But we're going to say that we do not have precision because we see a lot of spread, right? These are not consistent, right? These golf balls are very spread out. So as we're going through and we're looking at our sampling distributions in the next few examples, we're going to be thinking about these ideas of accuracy and precision. Accuracy, again, is whether or not things are correctly estimated, right? It is unbiased. And precision has to do with variation, has to do with spread, right? How consistent are the results that we are getting? Right, a sampling distribution is a special name for a probability distribution of a statistic. It's used to make inferences about a population. Sampling distributions give us a lot of different information. It gives us all of the different outcomes for the statistic, the probability of each outcome occurring, how often we can expect to see particular values of our statistic, and characteristics like bias and precision. So in this next example we're going to go through, we're going to discuss a sampling distribution, kind of walk through all of these different pieces of it. This is not anything that you're actually going to have to do in the homework, but it does give us an idea of what we go through or what we want to think about when we're thinking about finding samples in statistics. Right, so in this example, we have a small population of 6 people. 2 are cat people and 4 are dog people. Right, so we're going to represent our population by this D1, D2, D3, D4. So those are all dog people, and C1, C2, those are cat people. We're asked to find our population parameter for our percentage of cat people. Right, so our population parameter, our P, right, if we look at this, we have 2 cat people out of 6. Which reduces to 1/3, or as a decimal, we could write it as 0.333. So again, our P without any sort of extra notation, right, represents our population. Looking at our table underneath, notice that in here we're looking at our P hat values. Our P hat values come from our samples, right, so that's why we're thinking about our sampling distribution. Right, so in this table, we have 15 different possible samples. So what we've done is we've taken out of that population of 6 people, we've written down every possible combination that we could come up with if we were to take samples of 4 people, right? And now we're going to look at all of these different combinations and find our proportions for each individual one of these. So one possible sample that we could take is that we end up picking out of these original 6 people, we end up picking 4 dog people. Right? So in this case, we do not have any cat people. So our P hat would be 0. If we look at our next sample, well, we've taken 3 dog people and 1 cat person, so we get 0.25. Our next example, in our sample, we also have 1 cat person, so also 0.25. And if we continue to look down this column, each of these different samples, we have exactly 1 cat person. Right? So all of these is a 1 out of 4. Right? So all of these have a proportion, a sample proportion, a P hat value of 0.25. Now, if we look at this column over here, our first sample also has 1 out of 4, so this is 0.25. If we look at sample number 10, well, now we have 2 cat people. 2 out of 4 is 1/2. 1/2 is 50%, so we get 0.50. Right, if we look at all of the rest of these samples, all of these have 2 out of 4, so all of these are 50%. All of these have a P hat value of 0.50. Right, now we want to find our mean. Right, and there is one small typo here. Instead of being a sigma x, we should have a sigma p hat. So what we're going to do to find our mean, just like anytime we want to find our mean, going back to chapter 3, we add up all of our different values. So if we were to take our calculator and add 0 plus 0.25 plus 0.25 plus 0.25 plus 0.25, add all of the rest of these values, and then add all of these values over here. If we were to add up all 15 of these different decimals that are in red, we would end up with a total of 5.00. Remember, sigma means to add these up. So if we add up all of these numbers that I've entered into this table in red, we get 5.00. Then when we're finding our mean, we divide it by the total number of different values that we had. Well, we had 15 different samples. So we divide this 5 by 15. If we divide 5 by 15, we get 0.333, right, or 1/3, which notice is the same as our p that we had up here. Right, so our mean that we have down here of all of our p hats is actually the same as our p value that's up here. Right. What this is going to mean as we're looking through some of the next few examples is that our sampling distribution is unbiased. Right? Unbiased means it is accurate. Right. So the top of the next page, we are going to show our sampling distribution as a table and as a graph. Right. So looking at our table, we're going to go back and use our information that we have here, and we're asked for a few different things. We're asked for how many different times we have a 0 show up, how many different times we have a 1/4 or 0.25 show up, and how many different times we have our 0.5 or 50% show up. So looking at our table, we have exactly one value, that's a 0. So our probability of getting a 0 is going to be 1 out of 15. 1 out of 15, if we change it to a decimal, gives us 0.067. Right, we're dividing by 15 because that's the total number of entries that we have. Right, now we're going to look for a 0.25. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 out of 15 is going to give us 0.533 if we change that to a decimal. And then we're going to look at our 0.5. Well, we have 1, 2, 3, 4, 5, 6. 6 out of 15. If we change it to a decimal, it gives us 0.4. When we're showing these sampling distributions, these are like our discrete probability distributions that we saw in the previous chapter. We're just going to draw some lines that go up to each of our different probabilities. So for 0, our probability of our outcome is 0.067. Right? So if we draw a vertical line, that's going to be just short of here. Right? Because 0.1 would be 10%, that's about 7%. Right, 0.25. Well, on our sampling distribution line down here, 0.25 would be here, and we're going up to 0.533. So we're going to draw a vertical line up just a little bit past our 0.5. Right, and then our possible outcome of 0.50, we're going to draw a vertical line up to 0.4. So our probability distribution we can represent as a table. We can also represent our probability distribution as a graph. All right, so kind of connecting all of these ideas together that we've talked about so far. Bias and precision are something that we want to look for in our sampling distributions. We've already seen in our table that based on our sample, right, our statistics are going to vary. Right? Our p hat is not necessarily always the same as our p. What we're thinking about and what we want to focus on here, right, is how we find our bias. Our bias is measured as the distance between our mean value of our estimator, right, and the population of our parameter. So as we're looking at this and as we're going through these simulations in the next couple of examples that we're looking at, We are going to be thinking about bias being measured as distance. We're going to think about that as being a difference. So a difference meaning that we are going to subtract our mean of our p-hats from our p. And we'll see kind of exactly what that means after we go through a few of these simulations. Right, so our bias we're going to use as a difference, and it's between our mean value of our estimators and our population parameter p. All right, precision. Right? Precision is measured using our standard deviation, right? Because we said precision was tied to the idea of consistency. Consistency is tied to the idea of spread. Right? What we're going to do is we're going to, instead of referring to it as standard deviation, starting in this chapter, we're going to have a different formula that we're going to use that is going to be our standard error. The standard error measures how much an estimator typically varies from sample to sample. Right? When our standard error is small, we say the estimator is precise. And what we're going to see as we go through the next few simulations, the larger the sample we have, the more precise estimators we get. Right? So what we're looking for here is we're looking for standard error. And more specifically, if the standard error is small, then we want to say that the estimator is precise. Okay, so we're going to go through and look at a few simulations here. So in each of these different simulations, our P, our population proportion, is 25%. 25% of our population are cat people. So thinking about this before we get started, we want to answer a few questions. Will each of our samples contain exactly 25% cat people? No. Our sample statistics will vary. And is it possible to get a sample with 0 cat people? Yes, it is possible. Right? We saw that in the little simulation that we worked through on the previous pages. Right? Those numbers, those percentages that we got in our table, right? They varied. They varied between 0.25 and 0.50. Right? So our sample statistics vary from sample to sample. And one of those that we got in there did have a sample with 0. Right? So if we do have a sample with 0, it is possible, and it's going to continue to be the case as we're going through our few simulations that we're going to look at. All right, so in our first simulation, we have a relatively small population and a relatively small sample. So we're looking at a population of 8 people, and out of these 8 people, we're going to contain or select samples of 4 different people. Right? We were told that our P is 25%. So what that means in this case is that 2 out of our 8 people, or 1/4, 25%, of these people are cat people. All right, so if we were to do a sampling distribution, now unlike the previous example where we had 15 different values in our table, if we were to write out a table for this, we would have 70 different entries. So I didn't actually write out the table for this one because we don't need to find all those different 71s. Instead, we use technology to generate these results. And what we get here is that our mean is 25%, and our standard error is 16.4%. Notice that our mean is the same as our P. Right? So our mean of our sampling distribution is 25%, which is the same as our original proportion or percentage. That means that this is unbiased. Right? So underneath here, the part that's written in italics says that since this is the same as our original proportion or percentage, right, we have something that is unbiased, which is good. Our standard error is 16.4%. Right? So this measures the amount of spread that we have. Right? So we are unbiased, but that is actually a pretty large standard error. Right, now if we compare this to our next simulation. Well, in our next simulation, we have a population size of 1,000 and a sample size of 10. So our population size we've increased by quite a bit from 8 to 1,000. Our sample size, we went up a little bit. We're taking sample sizes of 10 instead of 4. Right? In this case, right, our P is still going to be 25%. So we're to have 250 people out of the 1,000 that are CAP people. We take samples of 10. Again, we're going to generate this using technology. Our mean is 25%. Right? Again, that's the same as our original P. So we are unbiased. Our standard error is 13.6%. Right? So notice that our standard error decreased a little bit from our last example. We went down from 16.4% to 13.6%. Right? This estimator is a little bit more precise than our previous simulation. And what this actually has to do with is our size of our sample. It's not necessarily the size of the population. In this case, it's the size of our sample. And we're going to see this as we compare our previous 2 simulations to this last one. Right, so now we're going to look at a population of 1,000 people, just like we did in the previous example, but we're going to take a sample size of 100. So we're going to definitely increase our sample size by quite a bit here. Our mean of our sampling distribution is still 25%. So we are still unbiased. Notice that our standard error has dropped. Right? We have dropped from 13.6% in our last simulation to 4.2%. Right? Again, this is a result of our sample size. That's the only thing we've changed between simulation 2 and simulation 3. Right, so taking these 3 different simulations, we're going to kind of summarize our results and then come up with a general conclusion. This general conclusion is really kind of the whole point of these simulations. Right, so our first simulation, our N, right? So this capital N means our population size, right? So this first row in all of these tables, we are looking at our population size, right? This lowercase n, this is our sample size, right? Our P is our population proportion, right? And our P hat is the mean of our samples. Right? In order to find our bias, again, we're thinking about a difference. We're thinking about the difference between the 2 different values that are directly above this. All right, so in our first simulation, our population size was 8, our sample size was 4, our population proportion was 0.25. Our mean that we got was also 0.25, and we said that this was unbiased because if we subtract these 2 values, we get 0. Our standard error, if you go back and look at the first simulation, our standard error was 16.4%. Our second simulation, we increased our population size by a lot, our sample size by a little. So we had a population of 1,000, a sample size of 10, and our population proportion was still 0.25. Our mean was still 0.25, and we said that this was still unbiased because these 2 values were exactly the same. Our standard error in the second one was 13.6%. Right, in our last simulation, here we had a large sample. So our population size was still 1,000. This time we took samples of 100 instead. Right. Our population proportion and our mean were still 0.25. So that means that this one was also unbiased because our difference is 0. But this one we said that our standard error dropped a lot to get 4.2%. So as we're looking at these, if we want to summarize our simulation, right, our estimator is unbiased for all sample sizes. Right, so all of these different rows in here we got 0. This was because the mean of the estimator, right, the mean of our p hats was equal to the parameter, which was our population proportion. Right? So we were unbiased for all of these sample sizes. Again, that's a good thing. We don't want bias in our experiments. Right. Bias, again, is a measure of accuracy. So our first statement here is thinking about accuracy. Our second statement here, we're looking at precision. Precision has to do with spread. Spread has to do with standard error. So our precision improves as the sample size gets larger. So we're going to say here that the standard error gets smaller as the sample size gets larger. Right? So the standard error gets smaller. There is less spread as our sample size gets larger. Our shape of our sampling distribution is more symmetric for larger sample sizes. If we go back to this previous page and we look at these two different histograms, right, this one kind of normal, kind of skewed, but if we look at this one is roughly a normal distribution. Right? So our shape of our sampling distribution is more symmetric for larger sample sizes, and we're just going to say we can see this by comparing the histograms on the previous page in our notes, which is page 10. The one with a larger sample size, right, is more symmetric. It's closer to a normal distribution. All right, so our conclusion, the whole point of these simulations. You don't necessarily need to remember the specifics of these simulations, but we did kind of want to go through and discuss a few things. But what I want you to remember out of this section, I want you to remember the idea of accuracy versus precision, right? Is something correct, right? Is it consistent? And how spread out it is. So think about your definitions of accuracy and precision, and think about our conclusion. Right? So this is the main other thing besides our definitions that I want you to remember from this section. So we're going to say the larger the sample size, right? So again, we're not necessarily worried about our population size, we're looking at our sample size. Right? So the larger the sample size, the more precise, right? Because our standard deviation, our standard error is smaller. So the more precise and normal the sampling distribution. Right, so the larger the sample size, the more precise, right, and normal our sampling distribution. Our standard error is smaller. We have something that's closer to a normal curve. This is going to be the key thing that we're going to use as we are going through problems in the next couple of sections. Right, we want to make sure that we have large enough sample sizes, right, unbiased samples, right, that are precise and normal to give us the kind of results that we desire. All right, so this last example here that we're going to look at, this last formula that we're going to look at, we are going to look at standard error. And we have a couple of conditions that are at the top, which are going to be similar to conditions that we're going to see in the next few sections as we progress through Chapter 7. Right? So if the following conditions are met, so if our sample is randomly selected, right? So we talked a little bit about simple random samplings. We want to make sure that our samples are randomly selected. Right? If they're randomly selected without replacement, our population must be at least 10 times larger than our sample size. This is also going to tie into some different stuff that we're going to look at in the next couple of sections. So basically that means that we want a large enough population and a large enough samples that are being taken for these. If that is the case, right, then our bias is going to be equal to 0. So our bias is going to be equal to 0. Unbiased is a good thing. Okay? And then the other thing that we're going to look at is we get a standard error formula. Remember, standard error has to do with precision. Right? The smaller the standard error, the more precise our sample. Right? So bias has to do with accuracy, and our standard error has to do with precision. Right? The smaller the standard error, the more precise, right, what we're looking at is. And then what we have down at the bottom here is a formula for our standard error. Right? P is going to be our population proportion, or if we don't know our population proportion, we can substitute P hat into our formula, which is why we have the second formula. The only thing that changes between these two is if we're using a population versus a sample, but our calculations are still the same. Inside our square root in the numerator, we have our proportion times its complement. Right? So whatever percent we have times its complement, we're going to divide that by our sample size, right? And then we are going to take the square root of it. If you were typing this into your calculator, you want to make sure and verify that you are getting correct results. Don't be afraid to use parentheses, whether you're using a scientific calculator or a graphing calculator. Right? It might be to your benefit to actually calculate what this complement is. Right? Put your numerator in parentheses divided by your denominator. Do that as one step and then take your square root. Or if you're doing it all in one step in your calculator, just make sure you're using parentheses appropriately and carefully. All right, so let's use this formula to find our standard error, because this is going to be a step of a lot of the problems that we're going to see in the next few sections. Right, according to the Mars Company, packages of M&Ms contain 20% orange candies. Suppose we sample 100 random candies. Right, what value should we expect for our percentage of orange candies? Well, we are told, right, that an average package of M&Ms contains 20% orange candies. So what should we expect? We should expect 20% are going to be orange candies. All right, our standard error. So in our square root, we start with our proportion or our percent up top in our numerator. I'm going to go ahead and write it as a decimal. So 20% as a decimal is going to be 0.20. Right? Then in parentheses, we're going to take 1 minus 0.20. Right? We're going to find the complement of that percent. And then we're going to divide it by our sample size. And in this case, we took a random sample of 100, so we're going to divide this by 100. All right, so I'm going to go ahead and do my subtraction. All right, so we're going to take 0.20 times 0.80 and divide it by 100. Right? If we want to, we can figure that out first. So if we take 0.20 times 0.80, I'm going to work through this and kind of show step by step. Again, if you want to shorten it using different steps in your calculator, you can. So we're going to get 0.16 over 100. 0.16 divided by 100, we shift our decimal place over. We get 0.0016. And then we take the square root of that. We get 0.04. Right, so our interpretations that we have here. We expect to get 20% orange candies because that was our claim. That was what we should expect. Right? And then what we just found here, our standard error, is our kind of range of error that we're going to get. Right? It's how much these are going to be spread out. So we should expect 20% orange candies, give or take 4%. Right? If we change this 0.04 to a decimal to a percent, then we get 4%. Right? So again, as you're looking through the section, we took some time in the middle to talk a lot about our different simulations. The actual details of the simulations are not necessarily your focus as you're going through this section. Right? You want to focus on your vocabulary words, accuracy, and precision. You want to know that our conclusion, right? The larger the sample size, the more precise and normal the distribution that we're looking at. And then you also want to feel comfortable with plugging stuff in and using this standard error formula, because as we move into the next section, we're going to use the standard error formula in pretty much all of the examples that we're going to go through and talk about.